set of R2. Okay, this set is a subset of R2. But what type of set here? The first element, the first coordinate must be 1 and the second coordinate is any real number. Okay, only those sets, only those elements of R2 are in this set in which the first coordinate is 1 and the second coordinate must be any real number, right? So the first coordinate must be 1, right? So only those type of elements are in this set. So the first element is 1 x with the operations defined by 1 y dash, that is equal to 1 is as it is, just we have to add second coordinates y plus y dash, and this is scalar multiplication k into 1y, that is equal to 1 ky is a vector space. So let x is equal to 1x, y is equal to 1y and z is equal to 1z belongs to V. We are trying to prove first of all closedness, that is x plus y, that is equal to 1x plus 1y, that is equal to 1x plus y. Now x plus y belongs to V. Why this x plus y belongs to V? Because the first coordinate is 1 and the second coordinate is any real number, right? Because x is real number, y is real number, so addition of two real number is also real number, so that's why this x plus y belongs to V. Next is x plus y is equal to y plus x, that we have to prove. So just starting from x plus y, that is equal to 1x plus 1y, by definition of addition, that is become 1 x plus y. Now x plus y we can interchange, right, because the commutative law in real numbers that we have. So 1 y plus x that will become 1 y plus 1 x, and that is equal to y plus x. So x plus y, that is equal to y plus x. Now the third, in bracket x plus y, associative law we are trying to prove, x plus y in bracket plus z, that is equal to x plus in bracket y plus z, that we have to prove. So x plus y, that is 1x plus 1y, outside the bracket is plus 1z, 1x plus 1y, that will become 1x plus y plus 1z. Now again using the definition of addition, 1x plus y plus z, right, and that can be written as 1 comma x plus in bracket y plus z, and that is equal to 1x plus 1 y plus z, and this is 1x is the x and 1 y plus z, that is y plus z, right? So we are prove, it's quite easy to prove that associative law for addition, x plus in bracket x plus y plus z, that is equal to x plus in bracket y plus z. The next question is what is our identity for the given vector space, for the given set? So identity means what? If 1 is identity for addition, then for any x belongs to V, x plus 1 is equal to x, right? That condition must be satisfied. If 1, again I repeat that if 1 is the identity, if 1 is the identity for the 1 is not a real number 1, right? Because just 1 is just a notation for identity. Okay, so if 1 is the identity for the given set V, then x plus 1 is equal to x, must be x, right? So just trying to prove that for every x is equal to 1x belongs to V, there exists 1 is equal to 1 0. Okay, there exists 1 is equal to 1 0 belongs to V, such that we will get x plus 1, that is equal to 1x plus 1 0, that is equal to 1, x plus 0, that is equal to 1x. Okay, that is equal to x. Similarly we can prove 1x is equal to x. Okay, similarly we can prove 1 plus x is equal to x. So hence 1 is equal to 1 0 is an additive identity in V. Next we want to check the inverse. For each x is equal to 1x belongs to V, there exists minus x, that is equal to 1 minus x belongs to V, such that x plus minus x is equal to 1x plus 1 minus x, that is equal to 1 x minus x, that is equal to 1 0 equal to 1. Okay, so similarly minus x plus x is equal to 1. Okay, so minus x is equal to 1 minus x is our additive inverse of the element x is equal to 1x. So this first 5 conditions are satisfied for addition. Next 5 conditions are for scalar multiplication. So alpha into x, that is equal to alpha into 1x, that is equal to 1 alpha x. Using this definition of scalar multiplication, you can see k into 1y can be written as 1 into ky. Okay, 1 comma ky. So that's why we use this definition of scalar multiplication. Alpha x is alpha into 1x, that is equal to 1 alpha x. That is also belongs to v, because 1 the first coordinate is 1 and second coordinate is real number. Alpha is also real number, x is also real number. So multiplication of two real number is also real number, right? So let next trying to prove distributive law. Let alpha belongs to R, then alpha into x plus y. That we have to prove that alpha into x plus alpha into y. So alpha into x plus y, that will become alpha into 1x plus 1y. Now x plus y become alpha into 1x plus y, and using the definition of scalar multiplication, we will get from this step to this step, we have to use definition of scalar multiplication. So 1 into alpha into x plus y, that will become alpha x plus alpha y, right? Because in real numbers we already have distributive law, so that's why alpha into x plus y can be written as alpha x plus alpha y. Now using the definition of addition, 1 comma alpha x plus alpha y can be written as 1 alpha x plus 1 alpha y, right? And next is using the definition of scalar multiplication, 1 alpha x can be written as alpha into 1x plus, and 1 alpha y can be written as alpha into 1y, that is exactly alpha x plus alpha y. So now we prove distributive law that alpha into x plus y, that is equal to alpha x plus alpha y. The eighth condition, that is also distributive law for two real numbers, for two scalars. Alpha plus beta into x, that we want to prove that alpha into x plus beta into x. So alpha plus beta into 1x using the definition of scalar multiplication, 1 alpha plus beta into x, right? Now this is distributive law for two scalar for real numbers that we already have. So 1 alpha x plus beta y, beta x, and 1 alpha x plus 1 beta x using the definition of addition, right? And 1 alpha x can be written as alpha into 1x plus 1 beta x can be written as beta into 1x. Okay, so alpha x plus beta x, right? So this condition is also satisfied. The next condition, ninth condition, associative law, right? Not associative law, but for distributive law for multiplication, right? For two scalar. So alpha beta x, that is equal to alpha beta into x 1x, that is 1 into alpha beta x. Okay, 1 into alpha beta x 1. Now distributive law for multiplication in real numbers, right? That we already have. So alpha into beta x, so alpha in bracket 1 beta x, that is equal to alpha into beta x, right? So the ninth condition is also quite easily satisfied. And the last condition, similarly we can prove alpha beta into x, that is beta into alpha x. Okay, 1 into x, that is equal to 1 into 1x, that is equal to 1x, that is equal to x. So thus all the 10 exams are satisfied by the elements of V, hence V is a vector space. So next question, question 3b, is the following set of vectors in P2 are linearly independent? That is the question. We have three polynomials, right? This is a shortcut method to prove that the given set of vectors are linearly independent or dependent, right? We have set of polynomial of we have three polynomials of P2. P2 means set of polynomial of 2 degree, right? And we know that dimension of P2 is equal to 3. Okay, in general dimension of Pn is equal to n plus 1. So we know that dimension of P2 is equal to 3, and we have exactly 3 vectors, right? So if you want to check that the given 3 vectors are linearly independent or dependent, for that we can also prove by definition that we know that v1 v2 up to vn, when we say that v1 v2 up to vn vectors are linearly independent, that by definition we know that k1 v1 just we have to take linear combination, right? k1 v1 plus k2 v2 plus k3 v3 up to kn vn, that is equal to 0 element, right? Whatever the 0 element in the given vector space V, if we take the linear combination k1 v1 plus k2 v2 up to kn vn, that is equal to 0. 0 means not real number 0, but that 0 means 0 vector. Okay, and if we if we get all the scalars k1, k2, kn, all the scalars are 0, then we can say that the given set of vectors are linearly independent. If suppose one of the scalar is non-zero, still the given condition is satisfied. For any ki not equal to 0, still you will get k1 v1 plus k2 v2 up to kn vn, that is equal to 0. Then you can say that the given set of vectors are linearly dependent. But that trying to prove this three polynomials are linearly independent or dependent, trying to prove by definition, it's quite lengthy, right? But because of we have exactly the number of vectors as the dimension, right, that's why we can use the determinant method. It's quite simple, because if the value of determinant is not equal to 0, then we can say that the set of vectors, set of polynomials are linearly independent. If the value of determinant is equal to 0, then we can directly say that the set of vectors are linearly dependent. So here we use that method. Okay, you can see the first row is coming from the first equation 2 minus 1 4. The second row is coming from the second equation 3 6 2, and the third row is coming from the third equation of the determinant, right? So 2 10 minus 4. The value of determinant, that is equal to 2 into minus 24 minus 20 plus 1 into minus 12 minus 4 and plus 4 into 30 minus 12. Okay, so minus 24 minus 20, that is minus 44 into 2, that is minus 88, minus 12 minus 4, that is minus 16 into 1, that is minus 16, plus 30 minus 12, that is 18, 18 into 4, that is 72, right? So minus 88 minus 16 plus 72, that will become minus 32. Clearly this is not equal to 0, so the given set of vectors are linearly independent. Okay, so here the half complete the solution. Thank you.